Okay, so welcome. Today we're going to be talking about rotational motion. But before we get into rotational motion, what I'd like to do is just do a little bit of review of circular motion. So let's consider our circle. So if we have an object that's going around in a circle and we draw the velocity vector at two different points, so there's point A, so there's the velocity, and then sometime later there's its velocity. Notice that I'm drawing the velocities tangent to the circle. What we know is that there must be a change in velocity. Even if there's not a change in speed, because the direction is changing, we have a change in velocity. So that means there must be an acceleration. And we went through this in class, but it turns out that the acceleration is equal to the velocity squared divided by the distance, the radius of that circle. Okay, so what we know is that since we know F net equals ma, so your sum of your forces equals ma, then what we can say for circular motion is the sum of the forces is equal to mv squared over r. And whenever you're dealing with circular motion problems, you are going to be basically setting up your F equals ma for the circle. So let's talk about an object that is just spinning around in a circle again, but let's take a different look at it. So it's going around a circle of the circle r, and let's say it spins around through angle theta. And so what we want to do, and it's got a radius r, we want to describe that arc length. So we know that theta is equal to that arc length divided by the radius, so we can rearrange this and we can say that the arc length is equal to theta times r, okay, or SOR, as you guys learned that in math class. Now, since velocity is really a displacement divided by time, what we can say is that this is equal to r times theta over time. But what we're really looking at here is that it is a change in angle, and that divided by time. So this really right here is our angular velocity, which is given the letter omega. So we have velocity, a linear velocity is equal to the distance times the angular velocity. So those are two important relationships so far. Okay, so let's take another look. Okay, same circle, since we know that the acceleration is equal to, the centripetal acceleration is equal to v squared over r, and what we know is that v is equal to r times omega, we get r squared omega squared divided by r. And we cross off that r with one of those. We end up getting that the centripetal acceleration is equal to r times omega squared. Okay, but what we know is that omega, we also talk about omega being an angular frequency, which is the 2 pi divided by the period. And so if we plug in omega, what we end up getting is r times 4 pi squared over t squared. And so what we can say is the centripetal acceleration is also equal to r 4 pi squared over t squared. And this is useful if you're given the radius and also the period. And then what we can also do, if we're getting really crazy with this, is that we have a, and what we can plug in for a is that we get m r 4 pi squared over t squared. Okay, and that's, so that is our oh, excuse me. Yep. Okay. But we can also actually play around with this and say this is equal to m times v squared, which v squared was nothing more than r squared omega squared divided by the period. Okay, so obviously we have a lot of different ways of writing this. Now, just a little side note, that if you're an object going around in a circle, and so we said that the centripetal acceleration is just based on the fact that the object is going around in a circle, but you can also have an object that is, so this is the a sub c, that's the centripetal acceleration, but we can also have an object that is going around in a circle and its speed is increasing. So there'd be a tangential acceleration as well. Let's see, a tangential acceleration. So what we can actually say is that the acceleration is equal to r omega squared, that's the centripetal acceleration, so the centripetal acceleration, and the a sub t, the tangential acceleration, is equal to r times alpha, where alpha is the angular acceleration. Okay, so in order to actually look at the full acceleration, then you would actually have to do Pythagorean Theorem. So the total acceleration, so I'm just going to say a net is equal to the centripetal acceleration squared plus the tangential acceleration squared. So you could use Pythagorean Theorem because a tangent and an inward always make 90 degrees. So just like all of our kinematics equations, I won't write this down, but check out your reference tables. There is an analogous circular motion equation. And they all look the same, but just have different letters for the different variables for linear and circular. Okay, so now we're going to actually move on to talking about torques. Okay, so one thing that you'll notice in your IB reference tables, we were using the Greek letter tau, lowercase tau. The IB reference tables uses a Greek letter gamma. Okay, so this is the upper gamma. And you've seen the lowercase gamma, but just because I am a creature of habit, in this tutorial I'm going to use the letter tau. But just know that the tau and upper gamma are the same thing. So it's defined as the force times the perpendicular displacement, which turns out to be F times R times sine of the angle. And so if we have a lever here, and it's got an axis of rotation on the left-hand side, and we apply a force, well, that force is pushing it down. So we have a component going down, and it's also pushing it in. And so there's our angle. So it's not the full force that's actually causing this thing to rotate, since it's only able to pivot on the left-hand side. It's really this x component of that force that's causing it. And you can notice that is the opposite side of the triangle. So that's where we get the sine function. We also kind of showed you that there's this, you could draw this line of action. I have a hard time doing dotted lines on here. And you can use the perpendicular distance. So this could be your r perpendicular. And sometimes it's more useful to do the r perpendicular, and other times it's just more useful to find the perpendicular force, which in this case would be, actually, excuse me, I wrote it in the x. It's in the vertical, so we could just call it the y. So if the object's not rotating, just like if the object's not accelerating, if the object's not rotating, what we know is that the sum of the torques is equal to 0, which really means that what the consequence of this is that the torques in the clockwise direction are equal to the torques in the counterclockwise direction. So if we are looking at an example here, we have a seesaw-like device. So we have a fulcrum in the middle, and we have a box on this side. I'll call this M2, and then we have a box on this side. This is M1, and we have the mass of the object, the center of mass of the lever itself is, we'll call that M3, and we can describe those lever arms. This could be R3. Then we can show that there'd be the R1. And notice that I'm drawing them from the fulcrum itself. And this would be an R2. So notice that this force is down, this force is down, and this force is down. But the ones that are going down on the right-hand side provide a clockwise torque, and the ones that are going down on the left, or the one that's going down on the left-hand side, provide a counterclockwise torque. And so what we can set up is that we have the M1R1 plus M3R3 is equal to M2R2. Now I'm being a little sloppy here because I'm writing in as M's, but I'm not really talking about forces. Really, technically all of these are being multiplied by G, but you can see if you put G in every term, the G's cancel out anyway. So you could just look at the mass times the distance from the lever arm, the distance from the fulcrum. Okay? But what we also know is that the object is, if it's not rotating, it's also not accelerating up or down. And so what we can also say is we could say the sum of the forces is equal to 0. And the reason why this is important, we have a normal force here, which the IB calls that a reaction force R. So we have one force going up, so that reaction force up is equal to the m1g plus m2g plus m3g. So this is sometimes helpful if you need to do simultaneous equations based on what you're given. Okay, and then moving on to moment of inertia. Basically, the moment of inertia, which is given the Greek letter, is given the capital I, is basically a quantitative way to tell you how the mass is distributed. Okay, so we know that there's the sum of the mr squared. So if you have a bunch of point sources and you want to figure out the moment of inertia, you take the mass of each one, you take it, multiply it by the lever arm, and square that, and add them all up. And you could take a look at page 156 in the IB review book for other objects. And the important thing about this is that you do not need to memorize these moments. You will be given them if it's not point sources. And the point source equation is in your reference table. Okay, so just like the sum of the forces equals ma, the moment of inertia is our analogous rotational mass. So what we have here is the sum of the torques is equal to I times alpha. So we have the rotational analog of force, torque. We have the rotational analog of mass. That's the moment of inertia. Then we have rotational acceleration. Okay. We also have rotational kinetic energy. And once again, I'm not going to go through the derivation of this, but we have the energy kinetic, which is equal to 1/2 I omega squared. So just like 1/2 mv squared, 1/2 I omega squared. Okay, so if an object is spinning and moving translationally, so if you think of a bicycle wheel is spinning and also moving along the ground, if it's in motion on the bicycle, then what we can say is that the total KE is equal to 1/2 mv squared plus 1/2 I omega squared. So we can calculate that quantity. All right, and then the last thing is up is the angular momentum, and the angular momentum given the capital L is equal to I times omega. Okay, just like P equals mv, we have L equals I omega. And since it is a momentum and momentum is conserved, and it turns out it's a vector quantity, but that's neither here nor there, what we can say is that if an object has a no net torque, then the I1 omega 1 is equal to I2 omega 2. So just like you could set up M1 V1 equals M2 V2, or better yet, M1 V1 plus M2 V2 before equals the same after, we could set something up. So if you have a figure skater and they're bringing their arms inward, their moment of inertia is going down, so their angular velocity goes up. So, all right, so that's all for now. As you could hear, I have some other things to attend to. I will see you tomorrow. All right, thanks for listening. Bye-bye.